I'm from Codasip, and for those who don't know who Codasip is, so we're a company that produces an EDA tool for designing and customizing CPUs. And we use our own EDA tool to create a range of RISC-V processors. And CHERI is one of the examples of custom compute that we include in our CPUs. So, hence our involvement with CHERI. One of the things we look at is safety and security as well. And reviewing all of the various safety and security technologies a couple of years ago, we came to the conclusion that all the ones at the moment, non-deterministic, all of the same problems as previous generations of technologies, and CHERI was looking very promising. So we decided to go ahead and implement CHERI. And since then, we've been working closely with University of Cambridge and other partners, and yeah, here we are now. So what I'm going to talk about is the software ecosystem for CHERI. CHERI itself, okay, you've got the hardware technology, but without software to use it, then it's effectively useless. So you really need to build a good software environment to be able to leverage the security of it. So I'll talk briefly about software strategy, then I'll give some idea of where we currently are with the software for CHERI, all the stuff that's been going on, in terms of both microcontrollers and application core software, and then some words on where we're going. So in terms of software strategy, we have to think about the software impact. And as we heard earlier, as you go sort of more abstract up to the applications, then the amount of effort to port to CHERI becomes less generally. When you're looking at lower level software that's closer to the hardware, interacting with memory directly, then typically you have to do a lot more work. Even though that's still in the 1 or 2%, when you're talking about an operating system that has millions of lines of code, that's still significant effort. So there are exceptions, of course, as was also mentioned. So if you have language runtimes, particularly chip machines, that sort of thing, things that are interacting with pointers a lot and memory, then yeah, you've got a bit of effort to do in there too. So in terms of a sort of high-level strategy for CHERI, what we want to do is make it easier for people to adopt and work on CHERI systems. And to do that, really, as a community, we need to be able to provide at least some of the basic stuff that people can then easily build on top of. Now that typically includes things like, obviously, compilers, very specialist knowledge in there, toolchains debuggers, firmware, very low level code to initialize system, get things kicked off, operating systems, because CHERI has a major effect on the operating system itself. In all of this too, I would say, open source is generally something great to collaborate on because we can all work on it, it's all open, all usable. But there's certainly a role for commercial software and adoption on CHERI as well. I would definitely not want to exclude that. And as we mentioned, language runtimes, and also the infrastructure to allow software developers to use CHERI more easily. So that could be simulators, for instance. And then all the way down to the big items, like for instance on Linux, you'd want a whole distribution, particularly, with sort of key libraries and key packages. Again, all of these just make it much easier for people to adopt CHERI and take something off the shelf with CHERI CPU, get some sort of software environment up and running quickly, and then develop the stuff that really, well, as we mentioned earlier, distinguishes what their product is and gives it a unique value. So at the moment, we sort of have three development paths which are going on at the moment. So we've had the DSBD program going on for the last number of years, looking at Morello, and concentrating on the sort of high-end application processor. Very much a research processor, the Morello, but it's been instrumental in us, as Simon mentioned earlier, in being able to determine which parts of CHERI are really, the core of CHERI, if you want to call it that. In Codasip and obviously in University of Cambridge, we've been looking at CHERI RISC-V as well. On the Codasip side, we've been sort of concentrating on 64-bit application processors, sort of mid-range, high-end embedded, and mid-range 32-bit RISC-Vs as well. So, this is where our current interest is. But we're also really interested in making sure that CHERI is scalable from everything from the tiniest microcontrollers up to server-end chips. So, and then we have CHERI as well, which has been mentioned multiple times today. We're looking at the very small microcontrollers, the sort of reduced subset, RISC-V 32-bit cores. And this is a great thing about CHERI. It's absolutely scalable from absolutely tiny devices up to very large devices. There are subtle differences between each of the configurations, but that's really what they are. They're configurations between a larger superset. And I'm going to, Will mentioned there's CHERI V9 as well, which was the original work done by the University of Cambridge. And in fact, a lot of the software that we are currently working on and base our newer versions on was all founded in the Cambridge Computer Lab. So we owe them and their funders, DARPA, and everybody else a lot of gratitude for that. So language support. Well, obvious one we have at the moment is C and C++. So I've split this into the different architectures, because obviously we have ARM, we have RISC-V, and we have smaller RISC-V. Now, the versions are up there, but I don't mean that to be read as, we're later on than them, or they're not. Because each of the different software packages in each of the different environments are likely to have different patch sets. And it also depends on where they come from as well. So some of the work might have been started based on the Cambridge stuff. In Codasip, we've progressed the version of the compiler. And in CHERI, they have additional patches that neither of the other ones have as well. So, but what it does demonstrate that is, if we want to, ideally the situation we want to get to is where we pull all of our resource together. Because if we're all doing separate stuff, then that's a lot of wasted effort. Especially as a lot of this is common. Similar to the sort of open hardware model earlier, we want to concentrate on the common software together, and then the unique sort of selling points of each maybe type of core is can deal with that separately. So one of the things we want to do, and for instance why we've pulled the CHERI RISC-V up to a later version is one of the aims eventually is, particularly for the open source software, is to be able to get it in a state where we can upstream it. To be able to get it to an upstream state, we have to get it onto the latest branch of development, which is effort. And again, something that collectively we can do a lot better than everybody trying to maintain their own separate branches. Okay, there's also the other languages that we want to support. Obviously, if we just support C and C++, it's quite limiting in what people can use, a CHERI CPU for. Yes, there's a lot of code in C, but there's an awful lot of code in other languages as well. Obviously, we have the sort of newer languages, like Rust. There's already two Rust compilers for Morello, and it's certainly something that we want to put on RISC-V, and I think CHERI obviously as well too. It'll become, increasingly important in terms of software that's out there. a lot of new software is written in it, and that's a great thing. And CHERI and Rust, I think, are really good together. Then you have your traditional runtimes. So although the languages might be memory safe, you may have a runtime that's, written in C and C++, for instance. So we have work to do to get all of those transferred over to being CHERI protected. So, but in the Morello, the great thing about the Morello project and the DSPD funding has got us there a long way already. So moving them to another architecture should be a lot easier than starting from scratch. Obviously for toolchains, C and C++, one of the issues we have with C and C++ is we have a multitude of options, depending on the size of the system, whether you're dealing with Linux, for instance, or BSD. But again, there is a lot of work that we can sort of transfer between these various different versions. And then we obviously have the things like firmware debuggers, emulators as well. So the stuff that allows us to boot the chips, allows us to debug them, allows us to sort of actually develop on them as well. Again, this is just to show that, because of the different sort of segments that we're looking at, from the very small microcontrollers up to the server sides, we get quite a breadth of the software required and the packages. So obviously some of the stuff is definitely transferable between all CHERI variants. Some of them aren't. Some of them have their own environments, which are maybe easier to use. Some of them need something a bit more complex. So in terms of microcontroller software at the moment, concentrating mainly on operating systems. So we've had for quite a while, based on the work from Cambridge, free RTOS. We're also looking at sort of other open source software. RTOS is now Zephyr and ThreadX. This is something that we definitely want to look at, just to take existing software, which makes it easier for people to move their projects. And then we've got CHERI RTOS as well, which is sort of a re-envisaging of an OS to suit CHERI specifically. And this is really important too. So when we go on to application cores, it's harder to move people off the sort of common operating systems that you're used to. On sort of the embedded cores, we probably have more of a chance to migrate, some people at least. If they're not migrating an existing project, if they're starting a new project, then we can get them moving on to sort of OSs that are definitely leveraging more of the capabilities of CHERI. So I think it's a very admirable effort. For application cores, just to show a range of what we're doing at the moment. So we've had CHERI BSD and Morello for quite a while, on V9 RISC-V as well. There's work will go on to update this to the new ISA, which is the one Simon mentioned that we're looking to standardize on RISC-V. SEL4, so formally verified microkernel, has just been moved to Morello. And again, we'll do the work to bring that onto RISC-V as well. And then at the moment, a lot of our effort in Codasip is looking at Linux. So at the moment we have Linux up and running in a basic state. By pure cap, we mean pure capabilities, where every pointer is now a capability in the kernel, and we have spatial memory safety. So we've had Linux on Morello as well, but in hybrid form, so where it's still operating in integer pointer mode, but interfaces to pure capability user space apps as well. So just a bit more detail on CHERI BSD. Definitely the most advanced rich OS for CHERI at the moment, based on FreeBSD. And we've been using this as a model in terms of features and even how it's been implemented in terms of our Linux development as well. It's a lot more full-featured. It already has spatial and temporal safety, so there's temporal safety in user level. It's being looked at now for the kernel level as well. There's user level compartmentalization as well. We'll use C1AN as an abbreviation because compartmentalization is very hard to keep writing down every slide. So we have advanced features, hypervisor support. There really are over 10,000 memory safe user level packages as well. In BSD, and this is great because we can also take a lot of that work and use it for the Linux side as well. And there's also very much the sort of in development features as well. These are things that are really interesting in the case of Linux as well. You know, things like kernel compartmentalization. One of the ideal things we'd like to do in Linux is be able to compartmentalize off drivers, because these are the source of a lot of problems that we have in the kernel. There's also compartmentalization policy frameworks and some really interesting work on co-located processes as well, and compartmentalization. So these are all great ways of showing how CHERI can really protect the system, and it'll be great to be able to pull these ideas from BSD onto other operating systems as well. In terms of Linux, well, we're in a very early stage of development, particularly on the RISC-V side. We have a pure capability, sort of recent kernel going. We've started from the ground up for the kernel, but we pulled in the Morello Linux code wherever we could, so the ABI in particular. As I mentioned, Morello Linux currently has a hybrid kernel, but we are looking at doing a pure cap kernel for everything now. And we definitely have our roadmap going ahead. Linux itself is obviously quite a complex boot structure and software ecosystem, but we've already got all of this operational, at least to a basic level. In terms of the way ahead, well, what we're looking at the moment now is combining sort of particularly on, we have the application core software, we have the microcontroller software. So it makes sense, at least in the short term, to look at pulling together the common application core software that we have for Morello and CHERI RISC-V to get them all merged in a single tree. And then we want to align things like the compiler longer term to include CHERI and everything else as well. Within the CHERI Alliance, the CHERI Alliance is the obvious place to work on this because we are dealing with multiple architectures. It's also a nice independent place from various different companies and players. It's an ideal place to work. So at the moment in that, we're defining lightweight governance processes depending on the open source project. And this is really just about how things like patches are submitted, how we track issues, how we review things before putting in, and things like what the strategy is for upstreaming and pushing patches back. So, and that's where we are at the moment. So, thank you.